This is the second video on life assurance contracts, the subsection of contingencies in actuarial mathematics. So in this video, I'm going over benefits that are payable immediately on death. And I just wanted to make a quick note about the previous video, which was benefits paid at the end of the year of death. I ended the video with this deferred term assurance, but I did not write the formula for the variance. So I'll do that quickly. The variance of M, which is the present value random variable for deferred term assurance contract, which is defined as this piecewise function. This variance of this random variable M is going to be equal to M A X N term assurance double the force of interest deferred by M years for a period of n years for a life now aged X, capital A, because it is a assurance contract and not an annuity contract, minus M A X N all squared. And you can see that that takes a very similar format to the ones to pretty much all of the variance formulas that we've come across so far. Okay, so let's move on swiftly to benefits payable immediately on death, which is the main purpose of this video. Okay, so let's first talk about whole life assurances. So I'm going to write here whole life assurance. Okay, and for a whole life assurance contract, the actuarial notation is going to be AX with a bar. So a whole life assurance contract with the benefit payable at the end of the year of death was just AX, but now when the death benefit is payable immediately on death, we put that line on top of the A. Okay, so we have A bar X, and this equals to the expectation of V to the TX. So TX being the complete future lifetime of a life now aged X, and that's a random variable. Okay, and as you can see, if I'm taking the expectation of this in order to get the expected present value, then this is V to the TX is my present value random variable. And this equals to the integral from 0 to infinity, and this infinity can be swapped out with omega. And the integral is of V to the T, TPX, mu x plus t dt. Okay, and note here what has gone on. So V to the Tx is a function of a random variable Tx. It's a random variable in itself as well. Okay, and now when I take the expectation of some function of a random variable, what I'm essentially doing is I take that function of the random variable and then I multiply it by the PDF of the random variable. So the random variable in here being Tx, and the PDF of Tx is TPX mu x plus t. And I integrate that over all possible values for Tx, for the complete future lifetime of this person now aged X. And the possible values for that is any number between 0 and infinity. But we can use omega if we are given that the population has a certain theoretical life cap that we're assuming. So it could say like this population is not expected to live longer than 100, and we could then swap out infinity with omega, which would then be 100. Okay, so the variance for this whole life assurance contract payable immediately on death, so we have the variance of VTX is equal to 2AX minus AX squared. Okay, and by the way, I really recommend, if you haven't listened to part 1 of this life assurance contract videos, then watch that one first, because I'm going to skip over some understanding things in order to abbreviate this videos to the greatest extent that I can, just so that I don't end up wasting the people's time who actually do want to watch both. So if I'm skipping over things that you maybe think I should be explaining more, then go back to the other video. I might have explained it there. Okay, so similar things would be how we arrive at these types of variances, why this 2 is in the superscript here, and why most of them take this form, etc., etc. Okay, so let's move on to term assurances that are payable immediately on death. So here we have term assurance, and this, I'm going to have the random variable f bar. So I used f in the previous video for when the benefit was payable at the end of the year of death. Now, because we introduce bar typically in actuarial notation, I'm just going to introduce a bar for the random variable to keep some sort of continuity. But please note, you don't actually have to use whatever value, whatever random variable letters I'm using for these things. In fact, you often don't even have to write these random variables, but I'm still doing it. Okay, in fact, the only place where that does actually become useful is when, in later sections, when you're going to have to write the gross future loss random variable, and then you might end up having to define this random variable. So it is somewhat useful to know how I'm defining these random variables. It's just the thing that's not necessarily useful is what letter I use. That's unimportant. Okay, so this is equal to v to the tx when tx is less than n, and 0 when tx is greater than or equal to n. Okay, so let's understand this. When the life has a complete future lifetime that is less than the term of the contract, then I will be present valuing that lump sum payment by tx, which is the exact amount of time that this person has left until they die. Okay, when they are now currently aged x. So I must present value it by tx number of years. And if they live longer or equal to the term of the contract n years, they don't get paid out, which is why this is a term assurance contract. They're only covered for a specified term. Now, I can take the expectation of this random variable to get the expected present value for this contract, and I take the integral from 0 to n of v to the t tpx mu x plus t dt. These two formulae are extremely similar. The only difference is the bounds that I've used in the integral. Okay, and obviously you can understand that this n is for a term assurance contract, but for a whole life assurance contract, I don't bound the upper bound. It goes to infinity or to the maximum possible lifetime. Okay, so when I integrate this, the formula that I'm going to give for this is a bar x n with this 1 or this dash on top of the x. Okay, now the variance for this is variance of f is going to be equal to 2a bar x n minus a bar x n squared. Okay, now we go into an endowment assurance. So I'll write over here endowment assurance. I'm trying to cover pretty much all the formulae that you will need in order to write the exam, and obviously not just rote learning these formulae, you have to understand them. Okay, so this random variable h is going to be equal to f bar plus g, and g I used for a pure endowment in the previous video, and f bar I've used here for a term assurance that's payable immediately on death. Okay, and I'll explain why there's no such thing as a g bar in a moment. So this equals to v tx when tx is less than n, or v to the n when tx is greater than or equal to n. Okay, so why there's no bar on top of this g, why I have no pure endowment payable immediately on death, is because that doesn't make sense. Pure endowments are payable at the end of the term of the contract if the life survives to the end of the term. So it's payable on survival, it's not payable on death. So there's no such thing as paying this out immediately on death. It doesn't make sense for a pure endowment contract. So an endowment assurance that's payable immediately on death, that immediately on death refers to the term assurance aspect of the endowment assurance, not the pure endowment assurance. Okay, so if I take the expectation of h bar, I'm going to get integral from 0 to n of vt tpx mu x plus t dt, and then I'm adding to that vn npx, which is the expected present value of a pure endowment assurance, and this equals to a bar xn in actuarial notation. Okay, and this a bar xn equals a bar xn with this line on top of the x plus a xn with a line on top of the n. And note here, I have not added this line on top of the pure endowment because this pure endowment is not payable on death. It's payable on the survival to the end of the term. Okay, so I don't have such a thing as this line on top of a pure endowment. Okay, so now let's write the formula for the variance. So variance of h bar, okay, that looks terrible, h bar, this equals 2a xn minus a xn squared. Okay, now there are some other relationships that are important that you're going to need to know, and then I'm going to explain the claims acceleration approximation, which will relate our assurances that are payable immediately on death and assurances that are payable at the end of the year of death, as well as a further approximation with the uniform distribution of death. Okay, so first, just some other relationships that are important. I'll write those over here. So a x is equal to a x n plus n a x. Okay, so what's going on here? Why does this make sense? Okay, well, this ax is a whole life that's payable immediately on death. So if this is the lifetime of a person that's now aged x, then this term assurance contract, sorry, not term assurance, this whole life assurance contract payable immediately on death lasts for all of this time point until he dies. Okay, this is a term assurance contract payable immediately on death, so it lasts up until time point n. Okay, so it covers them in that time. This is a whole life assurance contract payable immediately on death, but deferred by n years. So it only covers him beyond that point, but for the rest of eternity, but beyond that point. Okay, so we can see that this whole life assurance contract is equal to the sum of the term assurance contract and the deferred whole life contract. Okay. Now another relationship that's pretty important is NAX is equal to AX plus N times by V to the N times by NPX. Okay, so why does this work? Well, drawing this timeline again, and this is time point, or this is when he's aged X plus N. So this contract covers him from X plus N onwards. Now, if I want to calculate this, what I'm basically doing, because this is a whole life to a life now aged X but deferred by N years, so the cover only starts after N years, so it starts there. Okay, so that's basically just a whole life assurance contract from age X plus N, but now I have to discount it to this time point where he's aged X. So I have to include the probability that he survives to age X plus N, which comes from NPX, and I also have to include the time value of money between those 2 points. And because there's N years between X and X plus N, I use V to the N to discount the assurance from there to there. Okay, and why do I have to do this? It's because AX plus N gives me the expected present value at this point in time. But right now, he's aged X in this formula, so I have to discount it in terms of time and probability by a further N years. Okay. Right, now, the claims acceleration approximation. This is very important. So I'm relating now AX to AX. Okay, so AX, which is the whole life assurance payable immediately on death, to a whole life assurance payable at the end of year of death. So this AX is roughly equal to V to the 1 over 2. I'm going to explain this in a moment, don't worry. QX plus V to the 1 and 1 over 2 PX QX plus 1 plus V2 and 1 over 2 PX, so 2PX QX plus 2 plus and so on. Okay. And this equals to 1 plus I to the 1 over 2 AX. Okay, so what's essentially happened in here is I've said that, okay, let me write here, this is claims acceleration. So this is the claims acceleration approximation. Okay, so if someone was initially in this year going to get paid at this end of year of death, okay, so or at the end of this given year, then I would have to discount that by 1 year. Okay, but if they paid immediately on death, then I'm essentially going to say, okay, I'll just assume that the death happens halfway through the year, and then instead of discounting it by a whole year, I'll be discounting it by half a year. Okay, so instead of using V to the 1, I'm using V to the half year. Okay, and that's the difference. So this is approximated by the payments occurring halfway through the year on average. So that's what I'm expecting. I'm expecting payments to occur in the middle of the year. That's a claims acceleration approximation to this whole life payable immediately on death. So I might have values for AX and no values for AX bar, but I need AX bar. And so I can use these values given that I use this approximation where I multiply these by 1 plus I to the half. Okay, and obviously you don't want to have to go through by writing this in the exam every time. So I'm going to give you a quick way to think about it so you can jump straight from there to there. Okay, so this is the way I think about it. If the start of the contract here is at time 0, okay, then this AX has all the payments that occur at the end of the year. So at time 1, at time 2, at time 3, etc., etc. But I need these payments to happen approximately half a year earlier. So I need them to be over there, roughly. Okay, now what would happen if those payments were roughly over there? It would mean, but I still use this formula, it would mean that my present value would move everything to time negative 1 over 2. Okay, and if this is now present valuing to time negative 1 over 2, but I need it to be the time value of money to be at time 0, then I have to future value it by half a year's worth of interest. So 1 plus I to the 1 over 2. Okay, I hope that makes sense. Maybe let me try to explain it again in case it didn't, and maybe I'll say it a bit differently this time and something will click. So if my payments were initially going to be happening at the end of each year, but I want them to be happening in the middle of the year, but I'm still going to use this AX formula, then if I shift this entire scale along to the left such that these payments line up with the middle of each year, then it means that the present value will be lining up, the start of this contract will be lining up with time negative 1 over 2. But I need it to line up with time 0 because I want the present value. I don't want the past value. That doesn't make sense. Okay, so I must future value it then. After I've present valued it to time negative 1 over 2, by using this, I future value it by half a year. Okay, I hope that made sense. Alright, now that's the claims acceleration approximation, and this works just the same for AXN. This is a term assurance payable immediately on death. So 1 plus I to the 1 over 2 AXN. There you go, where this is payable at the end of year of death. And for be careful of this one, for a endowment assurance payable immediately on death will be equal to 1 plus I to the 1 over 2 A X N, here term assurance, plus A X N there. Okay, so I haven't multiplied this pure endowment by 1 plus I to the 1 over 2 because it's not dependent on death. Okay, so this is going to pay out at the end of the term if he survives to the end of the term. This line here should not be okay. This is going to pay out at the end of the term whether if he survives to the end of the term. Okay, so I'm not going to multiply this by 1 plus I to the half to take into account the fact that he might die during the term, because that pure endowment is not dealing with him dying in the term. It's not paying out when he dies. So I don't have to change from when the payment was at the end of year of death to now being immediately on death, because this doesn't actually deal with his death, it deals with his survival. Okay, now another approximation that is useful is AX bar roughly equals I over delta, where delta is the force of interest of A of X. Okay, and there is a proof for this. To keep this video as short as possible, I'm not going to go through the whole proof, but I will outline it for you so that you have an idea of how to do it, and maybe you can try it yourself. But also note this approximation will also hold for AX n roughly equal to, okay, that looks whack, A roughly equal to I over delta AX n with that on top of the X. So this is term assurances. Okay, now the proof for this, what I do is I write this out in terms of first principles. So that's equal to the sum to infinity, and then from k equals 0, and it'll be k a x 1. But then he also has to survive to each of these, so he must also have a survival probability. So it'll be pxk. Okay, and then so just quickly so that you understand why I've done this. So he must survive from age x to k. So if k is 0, he doesn't have to survive any time period. This will just be 1. So this is for the first term in the summation. And then here I'll have a term assurance for 1 year. Okay, so if he dies in that year, then I'll present value it to the start of the year. Then for the next year, for the second year, he must survive to the start of the second year. So k will be 1. And then it'll be a term assurance payable immediately on death with a 1-year term deferred by 1 year. So it'll be just for that second year of life. Okay, and when he dies in that year, and then I'll sum all of these mini term assurances with a term of 1 year until infinity. Okay, now the step next is to use uniform distribution of deaths to simplify this thing. So use UDD. Okay, and then what ends up happening is you pull out a lot of terms and you get some I times V over delta, and then you introduce this back into this formula, and then things cancel, and you bring out an I over delta from the summation, and what's still left in the summation will be the formula for a whole life assurance contract with the death benefit payable at the end of year of death. Okay, so that's just a brief sketch of the proof. And then also note that for these, this is the last thing I'm going to say in this video, for these death benefits that are payable immediately on death for these life assurance contracts, if we're dealing with select mortality, the select mortality equivalents to these assurances are exactly the same. The only difference in notation, that's the only difference. The only difference is going to be in notation, is for these x's, I'll just write them as with a square brackets around them. That's the only difference. Okay, and then, okay, one other thing. If you're doing this from first principles, and you have to write them out from first principles, which is unlikely, but it is possible, because you never know, they can ask questions in any way, then you have to be careful with the select period and using the correct mortality and the correct probabilities that correspond with the mortality, whether it's in the select period or out of the select period, and that type of thing. So just be aware of that. Yeah, so that's it for this video. Hope you enjoyed it, and I'll see you in the next one.